Section 19.3 An Introduction to Vibrational Spectroscopy. The harmonic oscillator approximation for a diatomic molecule is this. The potential energy is equal to half kx squared. K is the force constant, assuming the bond between the two atoms is a spring, and x is the displacement of the bond distance compared to the equilibrium bond distance. Now we can write out the shortened equation. H psi is equal to E psi. H is the Hamiltonian. H is the sum of the kinetic energy operator and potential energy operator. So we apply the kinetic energy operator to psi. We apply the potential energy operator to psi. The kinetic energy operator is negative h bar squared over 2 mu. And over here, this is the second derivative of psi. This is the kinetic energy operator. Mu is the reduced mass. 1 over mu is equal to 1 over m1 plus 1 over m2. Now, if we solve this equation, we'll see the energy. The vibrational energy is quantized. The vibrational energy of a harmonic oscillator can be 1/2 h nu, 3/2 h nu, 5/2 h nu, 7/2 h nu, etc. So it can be expressed in this form, where this n is a non-negative integer. So n can be 0, 1, 2, 3, 4. This equation tells you the vibrational energy of a diatomic molecule can never be 0. It's always positive. The minimum vibrational energy is 1/2 h nu. Nu is the frequency of the harmonic oscillator. If we know the force constant K and the reduced mass mu, we can calculate frequency. Sometimes we can take the infrared spectrum of a diatomic molecule, such as hydrogen chloride. Let's say the infrared wave number of this is 2900 per centimeter, or 2900 reciprocal centimeter. That means we can put 2900 such waves within 1 centimeter, or 290,000 waves within 1 meter. So this wave number can also be written as 290,000 per meter, or 290,000 reciprocal meter. So given this wave number, you can convert it to the frequency. Well, because the speed of light is equal to frequency times lambda. So lambda is c over frequency, and wave number is the reciprocal of lambda. So that's how you relate frequency, wavelength, and wave number. Once you get the frequency, you can use this equation to calculate K, assuming you know how to calculate mu for HCl. The value of mu of HCl is slightly less than the mass of the hydrogen atom. So it's going to be slightly lower than 1 atomic mass unit. I think it's going to be roughly 1.6 times 10 to the power of negative 27 kilograms. And again, the SI unit for mass is kilogram, not gram. If you have a polyatomic molecule, if you have 3 atoms, 4 atoms, 5 atoms, for example, if you are looking at the carbon-carbon double bond in the ethylene molecule, well, then the vibration between the 2 carbon atoms often depends primarily on these 2 carbon atoms, right? And then to a much lesser degree on the other atoms. And in this case, to a much lesser degree on the hydrogen atoms. Now, what if you have a huge molecule, like a protein molecule, and if you're looking at a carbon-oxygen double bond stretching? So usually this vibration is localized on these two atoms, the carbon and oxygen. And usually we'll get a wave number that simply depend on the force constant of this CO double bond and the reduced mass that you can calculate with the mass number of carbon and oxygen. Now we know that there are multiple energy levels. We have half h nu, 3/2 h nu, and 5/2 h nu. At the room temperature, most molecules, if we're talking about diatomic molecules, most such molecules occupy the lowest energy level. It's almost always true, assuming the Boltzmann distribution. Furthermore, we can do a quantitative analysis. So N1 over N0 is the population in the first excited state. This is the number of molecules in the ground state. Or you may say, well, over here, the quantum number n is 0. The molecules have 1/2 h nu vibrational energy. And over here, n is 1. So these molecules have 1.5 h nu vibrational energy. We can compute the ratio between these two. This is the so-called Boltzmann distribution. The ratio between these two is e to the power of negative energy difference divided by kBt. What's the energy difference? Well, the difference between 0.5 h nu and 1.5 h nu is simply h nu. Pay attention to this negative sign here. So that means the higher the energy, the lower the population. So let's look at a few examples in this table. All right, let's compare this H2 molecule with the bromine 2 molecule. And you can see this wave number is 4400. This wave number is only 300. So basically it tells you the vibrational frequency of H2 is much higher than the vibrational frequency of bromine 2. And that means we have a significant difference here. So this is h nu, this is frequency. All right, and also we learned this difference between the lowest and the second lowest energy levels for hydrogen 2 is much greater than that for bromine 2. All right. Oh, by the way, this is frequency. This is wave number. Frequency is proportional to the wave number. Frequency is proportional to the wave number. So this number is, I would say, roughly 14 times this number. So this number should be also roughly 14 times this number. All right. Okay, now we can compute N1 over N0 at a given temperature. At the room temperature, you can see over here, if you look at this number, you'll see nearly all molecules, all hydrogen molecules, occupy the lowest vibrational energy level. Okay, so less than 1 out of a billion H2 molecules occupy the first energy level. However, for bromine 2, because h nu is much smaller than bromine 2, you plug in this equation, you know what nu is, you'll see the ratio is 0.2. So you have a significant number of bromine 2 molecules occupying the first excited state. All right, first excited state means the second lowest energy level, that means 1.5 h nu level. However, you can raise the temperature so that this ratio can be much greater than the ratio at the room temperature. Again, you're changing this t here. When you change this t, you change the value of this exponential function. All right, so if you compare this to at 1000 Kelvin, you will see many more H2 molecules occupying the second lowest energy level. So more than 1 out of 1,000 now. So over here, it's less than 1 out of a billion. Over here, this is more than 1 out of 1,000. Now let's look at the diatomic molecules again. They are not really a harmonic oscillator. If you have a harmonic oscillator, the potential energy is half kx squared. That means if you keep stretching the diatomic molecule, if you keep stretching the bond, the potential energy keeps increasing. But that's not the case in the real world. In the real world, if you keep stretching a bond, well, you know the bond is going to be broken and the potential energy should level off to 0. So there's a more realistic equation or more realistic model to describe the potential energy of a diatomic molecule. It's called the Morse potential, Morse equation, Morse model. So equation is here. This is the potential energy. dE is a constant. And then it's 1 minus an exponential function, and then we square this. In this case, unfortunately, we use this x not as the displacement. So this x in here is the bond distance. X sub e is the equilibrium bond distance. So unfortunately, I'm using x for two different things on the same page. Only because, well, I'm trying to follow the textbook, so you're not confused when you read the textbook. So again, over here, x minus x sub e is the displacement. All right, so if you look at this potential, it's not quadratic, so we say it's enharmonic potential. And then if you solve the Schrodinger equation with the enharmonic potential energy expression, you will actually get a similar expression for the vibration energy with a little bit correction here. So you see this one, this part is the expression for the harmonic oscillator. And then if you have an enharmonic oscillator, you just need to add some correction here. Okay. This correction is much smaller than this term. The inharmonicity is typically small. All right, it's typically small. But as you can see over here, this is n plus half. This is n plus half squared. All right, so if n is really large, this negative collection will become really important. So that means, well, if we are trying to make the harmonic oscillator approximation for diatomic molecules, no problem, as long as this quantum number n is small. If n is 1 or 2 or 0, 0, 1, 2, maybe fine. But when n is 10, okay, this second correction term becomes so important. I want to show you the picture of it. So, this red line is the actual potential energy surface of a diatomic molecule. And this blue curve is the quadratic function half kx squared. So this is quadratic, harmonic. The red one is enharmonic. All right, so the red one, the red curve is realistic. The blue curve is a simple harmonic oscillator model. Now let's say if x is very close to xe. X is the bond distance. Xe is the equilibrium bond distance. Now let's see. Look at this. These two red curves. The red curve and the blue curve. Well, they match with each other fairly well. Okay, what if we stretch the bond to here? Okay, look at the potential energy of the red curve. All right, right here. Look at the potential energy predicted by the harmonic model. It's right here. So it's, I would say the difference is huge. And also, when n increases, we say, well, the molecule vibrates more vigorously. We have larger n. And when you have a larger n, again, we have a more negative term. So that's why you see this energy levels. At first, they are evenly spaced. And over here, the difference is roughly 1 h nu. So between 0.5 and 1.5, that's just 1 h nu. between 1.5 and 2.5, another h nu, h nu, h nu, h nu, h nu here, h nu here. But when I keep moving the mouse cursor up, you'll see the energy spacing gets smaller and smaller. Well, because of this negative terms. Now you have larger and larger n, so right here, eventually the energy spacing will become 0. So that's when this term and this term cancel. Well, it's possible, and in that case, there is no longer a bond. The energy is continuous, and you have two free atoms. There's just no vibration energy at all. All right. Now let's look at this d sub e. This d sub e has a physical meaning. This d sub e appears here as well. Part of the harmonic model. This d sub e is simply the depth of the potential energy well of a real diatomic molecule. So if you have a real molecule, the potential energy curve looks like this red curve, and you can define the depth of this potential energy well. This is d sub e. And also there's a term d sub 0. If you compare d sub 0 and d sub e, well, they look similar to each other. The only difference is here. Okay, so there's a small difference. This small difference is the lowest possible vibrational energy. And why is that? Well, d sub 0 is a bond energy. D sub e is the depth of the energy well. So why do we need these two different definitions? Okay, again, d sub 0 corresponds to the bond energy. So it's the amount of energy required to break a bond, right? But I'm going to tell you that bond intrinsically has this amount of energy already, roughly half h nu. Okay, it has this half h nu energy already. All right, so you don't really need an energy of d sub e to break the bond. You just need d sub 0 external energy to break the bond, because the bond has already had this half h nu energy. Oh, okay, so that's the difference. So I would say dE is greater than d0. The difference is roughly half h nu. That's the lowest possible vibration energy. Sometimes it's called 0 point vibration energy or 0 point energy. So if you hear 0 point, that means lowest possible. 0 point vibration energy is the lowest possible vibrational energy. Okay, when x is approximately equal to xe, that means the bond distance is roughly the same as the equilibrium bond distance. So we are looking at this small narrow region. We can rewrite this equation. Okay, we can expand the exponential function. Remember, exponential function e to the power of x is expanded into 1 plus x squared over 2 factorial plus x to the power 3 over 3 factorial as the Maclaurin series of an exponential function. So if I do that here, and if I neglect the terms with very high powers, again, if x is very close to x sub e, and then this guy squared or this guy cubed are really small. So I'm going to keep only two terms of the Maclaurin series of this function, which is going to be 1 minus alpha times the displacement. So you have 1 minus alpha times the displacement. Okay, so it's going to be just alpha times the displacement squared. So this is a approximation to this Morse potential. This approximation is accurate only if x is very close to x sub e, or the displacement is very small. The reason I do this is because I want you to look at the equation for harmonic oscillator. Alright, so when x is very close to x sub e, and then you compare the Morse potential and harmonic potential, you realize they share this x minus xe squared term, x minus xe squared. So really this k is proportional to d sub e. Alright, and d sub e is very close to d sub 0, the bond energy, so in general we say k is approximately proportional to the depth of the potential energy well or the bond energy. Again, this is because the bond energy and the depth of the potential energy well are really close to each other. So d sub e and d sub 0 are roughly the same.